So our first team that's going to present today is the HVAC design team. This team is advised by Dr. Vern Ulrich, and it consists of mechanical engineers Rachel Alt, Cameron Drake, James Hancock, Jared Hurd, Molly Marino, and Hannah Walsh. Hannah, I think you have the slides, so whenever you're ready, you can go ahead and start. Thanks, guys.
Okay, good evening, everybody. Thank you so much for coming. My name is Hannah Walsh, and I'm going to be talking to you all a little bit about some of the background of our project, as well as some of the goals that the team has had for this past year. So to start off, Crawford Hall is a 4-story administration building here on campus. It is over 35,000 square feet, and construction of the building started in 1937 and finished up in 1938. It's a home to a variety of different offices here on campus. The ground floor is home to campus safety, the registrar's office, as well as financial aid. The first floor has the president's office, as well as the admissions suite. The second floor has financial services and student employment. And the third floor is home to the Institute of Faith and Freedom. The fourth floor, or the tower, is home to the Collegian, which is the student newspaper here on campus. In addition, Crawford has a 1,000-seat auditorium on the first floor that is used for overflow chapel attendance, as well as other special events here on campus. So the project scope is essentially to design an HVAC system for Crawford Hall. The team wanted to look specifically at designing a central air conditioning system for the building, and also they wanted to look at the existing steam heating system and determine whether or not that needed to be updated. And this is the concept for how we went about completing this project. The first step that the team had to complete was obtaining drawings from Grove City Operations and conducting a site survey of the entire building. Once we completed the survey, we took our survey notes and the drawings from operations and modeled the building in Revit, which is a built-in information modeling software. After that, we performed heating and cooling load calculations in a program called TrainTrace 700. Once we got those numbers from Trace, we selected a HVAC system for the building. The team ended up going with a combination system that was a variable refrigerant flow, or VRF, combined with a dedicated outdoor air system, or DOAS. Once we selected the system, we were able to design piping and ductwork for the system to connect all the rooms together and model that in Revit. These are some of our goals for the semester, or for the entire year. As you can see, the first semester we focused mainly on doing the site survey, learning Revit, and completing the model of the existing conditions. And then in the spring, we focused on doing our load calculations, selecting the system and equipment, designing and modeling our piping and ductwork. We did this because it was very important to the team to create a very robust model in the fall semester so that we knew everything was right before we got into some of the calculations with TrainTrace. As you can see, we were able to complete all of our goals, some of which we even completed ahead of schedule, which was great because that gave the team a little bit more time to work on other parts of the project that were taking a bit longer than expected, which allowed us to still complete all of our goals on time. And with that, I'm going to hand it over to Jared to talk about site survey.
Hello, my name's Jared Hurd, and I'm going to talk to you a little bit more about the site survey and also Revit modeling. So the first step of our site survey is to acquire the drawings of Revit. To the right here, you can see a drawing of that. The building was originally built in the 1930s, and so the drawings were from that time, and there were a couple of renovated sets as well. In these renovated sets, they didn't capture every renovation that they've had in the building, so it was important for us to go in and compare the renovated sets of these drawings to the actual physical building to determine their accuracy, determine the renovations, what dimensions got changed, and how the rooms are now separated. One of the tools that we used during this is Bluebeam. So this software allows us to get a certain dimension for, like, say, a room, and then it allows us to set the scale of the drawing on the computer and extract all the other drawings dimensions. This lent itself very helpful whenever we were building the model in Revit. The last part of the site survey that we had to conduct was identifying the current HVAC equipment needs. And this included checking the steam piping system that currently was in Crawford, and also the cooling needs that the building will need, as well as like the space requirements, the ventilation space requirements for spaces such as the auditorium. And then finally, the space needed for renovations. So this is like the space in between the floors, or how the piping networks would run, or ductwork that we would design. So next, the architectural Revit modeling. This is our model to the right here. You can see a 3D image of this. This is the physical structure of the building. It is relatively accurate, where we could use this to provide the school with updated floor plans, as well as the work that we did with the HVAC system. It would allow us to be organized when we were making zoning plans, where we could give room number assignments to each of the rooms, as they were not labeled for either their purpose or just a number in general before we started our work. And then also, this allowed us to have easy area calculations. So that way, whenever we were entering our information into Trace, that we would be able to make sure these were correct. The next part of Revit modeling is the systems component of this. This is where our design actually comes into play. On the right, you can see the building with some ductwork, and also some piping and some interior units. So the existing steam piping was drawn, and as well as you can see our designed VRF piping, and then the green units of the interior units for the VRF. On the right, you can see the ductwork that is in the ceiling of the auditorium. And then also, not seen in these pictures, but in more detail later in our presentation, you can see the outdoor units that are modeled as well. With that, I will be passing it on to Cameron, and he will talk a little bit more about the DOAS and VRF.
Thanks, Jared. Hi, my name is Cameron Drake. So talking a little bit about the systems we chose, and just going into depth on those. We chose 2 designated outdoor air systems. This was due to the sizing that we needed for the building, as well as the 5 variable refrigerant flow systems. And then the building already had a built-in central steam heating system. Just talking a little bit about what variable refrigerant flow systems are. They are a large-scale ductless HVAC system. I'll talk a little bit more about why we chose them. But basically, there's an outdoor system that compresses the air and then sends it to the indoor units that there will send out the variable refrigerant to the needed units inside each room or zone, and therefore it will cool the building. The refrigerant used is R410A. It has an energy efficiency rating of 15 to 20. This is important because we wanted to make the building as efficient as possible. So when we did that, the refrigerant was a very important part of that. Looking at the variable refrigerant flow system, it can save almost 30% energy costs. This is huge, especially because we wanted to make it as efficient as possible. Looking into that, we knew that it was going to make it efficient, so we chose this system for that reason mostly. The reason why it is so efficient is because it's able to receive feedback from the rooms individually and cool them based off the needs of the rooms, as well as it's able to slow down its compressor, as well as pick up needing based on the room's feedback. So a few things of why we chose the VRF system. As Jared had mentioned, there's not a lot of room inside the building since it was built in 1937. So they didn't really plan for any ductwork or anything like that. So there wasn't a lot of space between the floors or inside the walls. James will talk a little bit about the cooling load later, but we realized that there was going to be a lot of coolant needed to be pushed throughout the building. So we knew that there was going to be a large cooling load needed. Therefore, we needed something that would be able to manage that and cool the building throughout the summer months. We knew that there was a central steam heating, there was a central steam heated furnace that pumped steam throughout the building through piping. So we knew that there was existing channels and ways to get throughout the building. So we kind of used that as a skeleton for our model. So that way we could use those channels to get us throughout the building. As well as it was energy efficient, like I had said. And another big reason was it's easy to install throughout the building. So we knew that we wanted to preserve the building's architectural structure and obviously not damage any of the old existing walls or ceilings. We also went with 2 designated outdoor air systems, one of which is in the auditorium. We knew that there was some room to put ductwork in, as well as another designated outdoor air system for some of the rooms on the other side of the building where we knew there was room with drop ceilings as well. What a designated outdoor air system does, it's like your typical HVAC system. It compresses and cools the air outside and then feeds it through ductwork into the building. It supplies dehumidified cold air to cool off the building and keep the building from being humid. It's used to ventilate the building on the office side of the building where we don't need it to cool as well. So it controls both the sensible and latent heats. This is used obviously since we have the VRF system in the office buildings. It doesn't need to cool as well. So James is going to talk a little bit about how we came up with the loads.
I'm James Hancock. I'm going to be talking about the equipment selection and the sizing that we did. So we spent most of the spring semester using TrainTrace 700. Trace is a design and analysis software program that helps HVAC professionals optimize the design of a building. Basically, you tell Trace the size of all the rooms in the building, what the walls and roof are made out of, where the sun is shining, what the weather is like, and it gives you a full-scale report of the amount of ventilation, cooling, and heating that you'll need in order to meet the demands of the building. So this is what the interface looks like, and it's also an overview of the different selections we made. So we selected the appropriate climate based on our location. We made numerous different templates based on the wall and roof construction, the location of the rooms within the building, and the desired heating and cooling temperatures. And then we used these templates to create individual rooms, which we divided up into different spaces of the building. Then we created 5 cooling systems and assigned the rooms to each one of these systems. After we made these inputs and ran our calculations, we had to run Trace, and it provided us with numerous different results sheets. For our project, the systems checksum sheets and the zones checksum sheets were also particularly helpful in determining the correct sizing for the system and the equipment. So this is an example of what the system checksums report looks like. This is the report for the auditorium. There's 3 main steps in using the numbers from this checksums report to select the equipment that we needed. So first, we had to size the dedicated outdoor air system, or DOAS for short. This is the separate unit that would provide ventilation to the building. So the way that we sized the DOAS was by looking at the total ventilation airflow measured in cubic feet per minute, or CFM. And that's in the blue square. And then the optimal ventilation cooling load is also looked at, and that's in the red square. So you can see there's a lot of different information on this sheet, but we were really just focused on those 2 numbers for making our selections. So we did this for each of our different cooling systems, and from the results, we determined that we would need 1 DOAS unit to support the auditorium and 1 to support the rest of the building. We selected the larger Mitsubishi model, which could handle up to 5,000 CFM for the auditorium, and the smaller Samsung model, which could handle up to 2,000 CFM for the rest of the building. So the next step was to size our outdoor VRF units, or the variable refrigerant flow units. These are the units that are placed outside and would supply the refrigerant to the numerous indoor units. So the way that we sized the outdoor units was by looking at the non-ventilation cooling loads on the system checksums report. So this is a different report than the one I just showed you. So the units had to be between 6 and 16 tons each. And we determined based off of this that we needed to select 3 units for the auditorium and then 2 units for the rest of the building. We wanted to stay with one manufacturing brand as much as possible, and Mr. BC provided an extensive lineup of VRF equipment, so we decided to stay with them. We selected the R2 series N generation outdoor units for all 5 of our units. We had 3 14-ton units for the auditorium, and then 1 16-ton unit for the ground, north and south systems, and then 1 12-ton unit for the upper floors. So the third step was to size the indoor VRF units. These are the units inside the building which distribute the air to the rooms. Instead of using the system's checksum report, we actually had to use the zone checksums report and look at the supply air CFM and the cooling load for each of those individual zones of the building. The indoor units could not be more than 4 tons each. So some of the zones, such as the auditorium, needed multiple indoor units. So we selected 3 different types of indoor units. We had ceiling cassettes, which were used when we had drop ceilings available and we could install those directly into the ceilings. We had wall-mounted units when we didn't have drop ceilings, and we had floor-standing units when we couldn't use the other 2. So we designed the system with the assumption that we couldn't place any of the heavy outdoor equipment on the roof because it wouldn't be able to support the weight of the units. So we chose to position the DOAS and the 3 outdoor VRF units for the auditorium outside the east wall on the patio that is between Crawford and the adjacent building next to it. And the other 2 units would go on the south end where there's already some existing mechanical equipment. And then the ductwork and piping networks were created in the Revit model to connect the DOAS and the outdoor units to the indoor units, which you can see in the picture to the right there. Finally, we had to size the ductwork and the DOAS fan. We sized the ductwork using a helpful online duct calculator. All you had to do was input the static loss and enter the airflow in CFM for each branch. And the calculator then provided the appropriate size for both round and square ducts. In order to supply the correct amount of airflow to the farthest point in the duct line, the DOAS fan was sized properly so that it could overcome the static pressure. We found that we found the equivalent duct lengths and then the fitting losses along the longest duct route, and we made those calculations and we added up all those values, which you can see in the table to the left. With an additional 15% factor of safety just added in, the static pressure was 0.13 inches of water, which is within the range for the DOAS unit that we selected. So I'm going to pass it on to Rachel to talk more about our system.
Hello, my name is Rachel Alt, and I will be talking about our system design and some of the problems that we encountered along the way. As was stated previously, we needed to estimate where the current steam system piping would be in order to not overlap with our VRF piping system. Therefore, from looking at where the current equipment was located within the building for the steam system, we then made an estimate of where we believed it would be, and then we designed our piping layout around that. When we were designing the piping network, we utilized our previous knowledge from fluid dynamics to the best of our abilities to try and minimize the losses within the system. Once we had determined what mechanical equipment we needed within each room from the train trace calculations, such as the ceiling cassettes, floor standing units, or wall mounted units, those were then placed within each room in our Revit model. In order to properly place those units, we had to also place the VRF piping system within the model, and these piping systems were placed using generic family pieces within Revit, such as T's, elbows, and piping. Here's a 3D view of the overall building from the mechanical equipment perspective. The ductwork for the auditorium is on the right, and you can also see the outside and inside units. It looks like they're floating in midair, but that's because you can see the ground floor, which would normally be under soil. So here's shown the auditorium looking from the northeast end of the building. You can see both the ceiling cassettes for the VRF system and the DOAS along the top, as well as the piping that runs underneath the first floor to connect to the steam heating within the auditorium. This slide shows the auditorium from another perspective, just to give you a better idea. Also on the right, you can see a top-down image of the ductwork and piping for the auditorium. So for the ground floor, the VRF piping network was placed between the first floor and the ground floor due to the large number of ceiling cassettes in order to make that an easier connection. Also within this view, you can see the steam piping network that we estimated connecting to its respective equipment, which are the small circles along the wall within this image, which are kind of hard to see. Within the first floor design, we decided to have the piping run between the first and the second floor so that the ceiling cassettes would be easier to connect as well. In here, the first floor is on the left. Go back. Sorry. Also, one thing we did was we moved the piping around the front lobby so as not to interfere with the aesthetics for visitors, since the front lobby space goes up into the second floor. For the second floor, the piping network was placed between the second and third floor so that it can easily connect to the wall-mounted units present within our design. And we also routed our VRF system around the current steam system so as not to interrupt that. Also, as you can see in the bottom left portion on the right image, there's a portion of pipe that sticks out of the building. That would then be run down the building to the second outdoor unit at the south end of the building that covers the load for the upper floors. For the third and fourth floor, the piping was run within the ceiling of the third floor to avoid cutting through the center portion of the stone surrounding the tower. We routed the piping around in order to cover the north side of the floor, and then we vertically connected the piping to properly cool the fourth floor or the tower. Also within this image, you can see the ceiling air ventilation units within the auditorium along with the ductwork. When we were modeling, one of the major challenges was designing the level of detail needed in both our Revit and train trace modeling in order to get accurate data so that the appropriate equipment could be selected. This included parameters such as building thickness and materials, square footage, average number of occupants in the area. The details of these parameters were often best estimates because when equipment is being selected, factor of safety calculations are made to make sure that the system will be able to handle the building's load. Therefore, in order to understand the detail needed to know which solution would be the best, we looked to the guidance of professionals from CJL. And so with the help of CJL engineers, the team was able to specify each of these parameters so that we could be confident in our solution. The largest design challenge that the team faced was caused by the architecture of the building, specifically not having room to place ductwork through the office side of the building. This resulted in the hybrid system that we had specified. This system designed utilizes an air system where needed and also where space is available within the auditorium. And then for zones where space is limited, the system uses the variable refrigerant flow, which requires very small piping compared to some other options. And this way we were able to overcome the lack of space issue, but we did end up sacrificing ventilation. The last design challenge that we encountered was when we were designing the piping and ductwork for the system. It was important for us to try to preserve the architecture of the building. So in order to accomplish this, the piping and ductwork installation areas had to be generally accessible in order to limit the amount of damage that would be done to the building during the renovation process. So in order to do this, we worked to run our piping alongside the current steam heating piping wherever possible, and this way we would be able to limit the number of areas where we would end up disturbing our architecture. Now I'm going to pass it off to Molly to talk about some recommendations.
Thanks, Rachel. As she said, my name is Molly Marino, and I'll be wrapping up the presentation this evening. So some recommendations we have regarding the whole design process and, of course, our progress across the academic year. We would like to improve the design quality. James had mentioned a second DOAS unit, and to really find the best place to place this unit, we would need to do a structural analysis on the roof to see if Crawford could hold the weight. Again, this building was built back in the early 1900s, so it was not built with heavy HVAC equipment in mind. Second thing we would do is update the existing steam heating. The system in the building, it's still functional, but it's pretty outdated. And from that, it leads to a lack of efficiency. And a third thing we would like to have looked more into would be an HVAC control system. HVAC controls, a little background briefly on that, they monitor the operation of systems within the building, and they assist in regulating desired temperatures based on sensors. So those are just some things if we have more time, we would have liked to look into. So the next thing I'll be talking about is a brief overview of our cost analysis. We have a variety of categories, and if you'll look at the bottom right-hand corner, I have a note that says our overall cost. It does not include demolition, HVAC controls, as I previously mentioned in the other slide. So here's just a brief overview of how much we're estimating things would cost. And we got these values thanks to CJL and their assistance in using an online software called RS Means, which gives a real-time values within the construction industry, which is how we were able to price different units. And if you look at the top right-hand corner, it says total O&P, and that stands for overhead and profit. That's just an estimate that describes the cost margin a builder would charge. This value, it includes the cost of the service plus their profit. And just a brief refresher, all these technical terms, DOAS stands for Dedicated Outdoor Air System, and VRF stands for Variable Refrigerant Flow. So going more in depth in our cost analysis, here's an example of how we priced our outdoor VRF units. As James and my team members said earlier, we had 5 units that we came up with. And if you look on the selection, they seem pretty similar, but where they differ is coming down to the size. Top left-hand corner, right beside systems, it says CL, which stands for cooling load. And cooling load, that's the amount of heat that needs to be removed from a space in order to maintain the desired air temperature that is set and the desired humidity level as well. So in conclusion, as Hannah mentioned earlier, we were able to meet all of our goals, and we're really excited about that, especially with COVID staying on our timeline. We were able to create an architectural model, which we spent a lot of time on last semester, as well as conduct load calculations, which we did early this semester. And from those load calculations, we were able to use them to aid in selecting a system. And from that system, we went back into Revit, we designed it, we put in mechanical equipment back into our architectural model. And from that model and our load calculations, we were able to perform a brief cost analysis just to hypothetically come up with a number. And from this, we would just like to give a shout out to campus safety and operations for escorting us around Crawford. There's some confidential areas in there, so campus safety helped us out with that, as well as operations. They provided drawings and just information about the building in general. Our advisor, Dr. Yu, who unfortunately can't be here, he's with the Baja team, but we're thankful to him for giving us the okay to do another HVAC project this year. And of course to our sponsors, CJL Engineering, and all the engineers that helped, but especially Christy Kramer for responding to our many, many questions during this process. And with that, we're open to questions.
So that's great. Good job, team. It's nice to see such a good design, and I'm glad you guys were able to work closely with CJL and get their professional input too. May I suggest that the team actually all turn on their videos, their webcams for this question session? And audience members, we've got lots of time here, so if you have questions for the team, why don't you go ahead and ask them, and we'll walk through those here.
Hi, this is Christy Kramer from CJL. I just want to say it was a pleasure to work with you guys over the course of this last year, and I think you did an excellent job, and you covered a lot of ground in a pretty short amount of time from start to finish. So just kudos to the whole team, and it was great working with you and being in contact with Molly. I guess my question is kind of a reflective one. Looking back over the year, what were some things that you really enjoyed or you really were interested in after working through it and can carry forward with you into the future? And what were some things that you would have scrapped or done differently, having gone back and done it again or started from the beginning again?
I was going to say, like, one thing that I realized, like, there's a lot of things that you kind of have to make estimates about. Some things are really important, other things aren't as important. And so just figuring out like which things to care about and which things not to. So for instance, like I spent a pretty decent chunk of time going through and looking at the drawings and figuring out like what each wall was made out of in every part of the building, which was kind of fun. Like I got to go around and kind of, look around different places and figure out what this wall was made out of versus what the wall downstairs is made out of, because we thought we were going to have to know like very specifically all those things for each part of the wall. But turns out we just ended up making 2 general estimations of what the wall text for our train trace results. So that was something that I didn't really know about, but I just wanted to kind of, look into it and was curious about it. So going back, I definitely wouldn't have spent all that time, really analyzing each part, but that's something I learned and that's something I can take forward.
Yeah, I would say for me, obviously I've interned with CJL, so I did come in knowing some information, but this project just really showed me that there are always things to learn in this industry, which is why I'm so excited to go into it after graduation. So I think I can speak on behalf of all the team that we realize between vocabulary and just technical terms and new technology, there's just so much out there. And we really enjoyed going back, looking at an older building versus, like a new high-rise tower. I think we enjoyed the challenge of Crawford.
Yeah, I can say for me, one of the things that just learning about the process, the part that I had known more about was the architectural modeling. And so I got to learn a lot more about like the actual engineering, HVAC engineering design process. And so just being able to get more involved with that and figuring that out was a big thing for me. I'm glad I got to do.
I think for me, I sort of came into it not having much experience within the HVAC field. And so I also was able to learn a lot about the process and realizing just how much goes into it that I didn't realize, like I hadn't worked with Train at all. And so learning all about that was definitely helpful.
Christy, and I don't know if there's others from CJL on the line right now, but just on behalf of the engineering school, thanks so much for your participation. You professionals interacting with the students is such an enriching part of their experience here, and hopefully you'll get good work out of several of these guys for years to come.
Thank you. It was our pleasure, and they're great to communicate with, and it was an easy go of it for us this year.
Glad to hear it. Are there other audience questions for the team?
Yes. Does the college have budget to actually install the system that was designed?
Great question. And we'd have to take that up with the Board of Trustees, but I'm just going to say no. So something challenging with Crawford, as we've talked about, is the architecture. And if you saw my numbers, we're coming in at $500,000. But once you put in demo, as well as HVAC controls and just some other things we didn't have time to look into, wouldn't be shocking if the sticker price was closer to $1 million. And the college has been dealing with no AC in Crawford, just window units right now. That's what's in there. So I think some people are okay to continue with the window units and put the money elsewhere, into incoming students, into education. So that's what I'd say about that.
Molly, as a quick follow-up, do you have any sense of how the cost would change if it was done in combination with a heat renovation?
Yeah, I mean, again, we didn't look too much into it, but anything like that is going to add on to the cost. And, you know, they've been using steam heating. So when you pick systems, again, like when we did the HVAC side with the VRF systems, if you do VRF versus more central air, VAV, like that all factors into cost. So I don't have a better answer for you.
I had a question for the team, actually, if you don't mind. I noticed that I was a little bit surprised at two things. Number one, it looks like your people represented 60% of your heating load, cooling load, but solar was only 10%, which I would think is very different than like a residential situation. Do you know if that's typical, or would you say that was somehow unique to Crawford because of its stone construction?
Are you referring to like on the checksum sheet? Or where
Yeah,
you see that number?
did I have that right? It just looked like the vast majority of the cooling load was actually from people.
Let me take a look at it just real quick again.
I was gonna say, Hannah, you could go back.
Yeah. That's one of the things we factored in was the people, and like part of the selection, just so people kind of understand, like the selection of like setting up trace is we had to orient the building. So understanding like that the sun rises and rises and sets in different places. And so but depending on the location or the orientation of the building, you're going to have more direct sunlight throughout the day. So I guess to answer your question, like the amount of people in there is going to be significantly more because this is the auditorium that we're talking about here. So this is, I'm not surprised that that's the case because it's the largest. So we sized the auditorium to seat the maximum amount of people. Of course, right now with COVID, like you're never going to meet that, but it can hold up to, I think, 1,200 people. So out of all the spaces in Crawford, I'm not surprised that it came out like to be that way. So.
Thanks. Yeah, that's interesting. You're right. I had missed that was just auditorium specific. Other questions for the design team? Okay, well, if there's no further questions, then maybe all audience members can unmute their microphones and clap at once. Let's see, that might get logistically challenging, but good job, everybody. Thank you very much for thanks very much for your hard work this year. It's a design to be proud of. Hopefully it'll get built sooner rather than later. And again, thanks to the external engineers who helped out with this.